Hi everyone. Today's topics are typed recursion and variants. You remember recursion, right? Recursion. We learned recursion before the midterm exam, and today we are going to add types to recursion. That's going to be the first part of today's lecture. During the second and the third parts of today's lecture, we are going to learn about variants. Variants. Now that you learn variants, you can define your own types. Types and laziness. We have been talking about types, and you should remember what lazy is, right? There are no lazy languages that permit mutation. There are several lazy languages. There have been several lazy languages, while there's only one meaningful lazy language called Haskell. Haskell is really cool. That is just the most important and the most widely used lazy language. All the other lazy languages that I've heard of died. 레이지 랭귀지가 여러 가지 있었어요. 그런데 지금까지 살아남은 유일한 언어가 하스켈이에요. It is really cool. And if you say, I am a Haskell programmer, when you are on the market, when you're looking for a job, then recruiters will think you are smart because you are a Haskell programmer. It's really cool. And there are no lazy languages that permit mutation, meaning that lazy languages do not permit mutation. Right? They do not allow mutation. There are no lazy languages without type system, meaning every lazy language supports type system, right? Right? Then why? In a lazy language, function calls are not necessarily evaluated in the order where they appear in the code, right? We saw that in that LFAE, even though we have some function call. When we evaluate E1, we are going to strict that so that we can have closure V value. When we have argument expression of the function call, right? We did not evaluate E2. We captured that, we froze that as it is, like X per V, with that expression E2 and the environment at that time. And remember that. And while we are evaluating the body, where this E1 is evaluated to closure V, the body of the closure V, when we encounter the parameter name, then we look up the environment to get X per V, and when we need the value of the parameter, then we evaluate it X per V. That was the laziness, right? So even though E2 appears here, we do not evaluate E2 at this point. We defer the evaluation of E2 until when it is needed. That was the main point of laziness, if you remember, right? But, for functions that perform side effects meaning they are not pure, they are not purely mathematical. They may have some effects like throwing an exception, printing something on the screen, or getting inputs. They are all side effects, not mathematical. It matters in which order they are executed. When your code has some side effects, it really matters whether you evaluate the code in the order or not, right? So lazy languages usually emulate side effects in special types that ensure that they are executed in the right order. That's why lazy languages always have type systems. Okay, let me repeat what I just said in Korean and then again in English and move on. 그래서 lazy language는 진짜 쿨한 언어예요. 여러분이 어디 나중에 잘 나가는 되게 똑똑한 프로그래머야. 쟤 되게 잘할 것 같아 라고 하면 하스켈이나 그런 쿨한 언어 조금만 할 줄 알면 돼요. 그런데 레이지 랭귀지들은 역사상으로 여러 개 쓰지만 유일하게 살아남았다고 불릴 수 있는 것은 하스켈이에요. 근데 어쨌든 지금까지 있었던 레이지 랭귀지들은 뮤테이션을 그죠? 뮤테이션을 허용하지 않고 타입 시스템을 가지고 있어. 왜? 뮤테이션이 없으면 원래 뭐 프로그램 돌다가 프린트를 하거나 인풋을 받거나 익셉션 트로잉 하거나 이런 여러 가지 사이드 이펙트가 있어야 실제 언어일 텐데 그런 걸 못해요. 뮤테이션이 없어서. 그래서 레이지 랭귀지는 그거를 흉내내요. 모나드라는 딱 쿨한 타입 시스템을 이용해서. 그래서 레이지 랭귀지들은 보통 타입 시스템을 이용해서 사이드 이펙트를 흉내낸다. In lazy languages, specifically Haskell, it does not provide mutation, but it simulates that by using some type system, usually called monad. Static and dynamic types. We have been talking about languages without types, actually dynamic typing, right? And now after the midterm exam and after the continuation, we are talking about static types. So we compare this static versus dynamic. Static meaning before running and dynamic meaning at runtime. So it's just running. It's actually executing, interpreting. Static meaning before executing at compile time. So static meaning really early error detection before running. And because we have some information about the code before running, we can optimize the code before running so it allows efficient execution. And types are better documentation of code than comments, right? Comments are in natural language and they are not really sync with the actual code because programmers are lazy enough not to fix the comment when they fix the code. And dynamic typing, it's dynamic, so it doesn't really have one phase before running. It's really quick. So it's good for rapid development and it is easy to adapt to changing requirements because it doesn't need all those types and type checking. So there are pros and cons. There's no free lunch. With static typing, it's really good for early error detection. If you have errors, you'd better detect them earlier than later, right? But it's kind of annoying because when you have Java programming or Scala programming or even Haskell, there are going to be lots of type errors while you're implementing something. But once the type system says, okay, your code does not have any more type errors, then it's highly likely that your code is correct. It does not guarantee that your code is correct, but it is highly likely that your code does not have severe problems. Dynamic typing, it's really good for rapid development. It's easy to change your code, but it does not check anything for you. So you need to take your own risk. So depending on who you are, 여러분이 어떤 사람인가에 따라서 depending on the problem that you're trying to solve, 어떤 문제를 푸느냐에 따라서 static typing may work better or dynamic typing may work better. In recent languages, they have both. Like Recursion is a dynamic language, but these days they have types. JavaScript is notoriously freestyle programming language. Anyone can write JavaScript code like even just 7 years old, but most JavaScript programs are really bad and wrong. So Microsoft has TypeScript, adding types to JavaScript. Facebook has Flow, adding some static information, static analysis on JavaScript. And Ruby is a dynamic language, and there is a Diamondback Ruby and more. There are many languages that have both static and dynamic types to take advantage of both words. And you may want to pick your own favorite language. Type check and interpret. We discussed this on Monday, but let's review. When you evaluate an expression with dynamic typing or say without any static typing, you just interpret it. Interpret the code under the empty environment. But if you want to check your code before running so that you can get rid of all those stupid runtime errors, you may want to have type check before interpreting it. So at type checking time, you can check the type of this expression without running under this empty type environment. When the type checker says, okay, oh yeah, under this empty type environment, when we type check this expression, we have some type tau, meaning that it's well typed, it does not have any type error, then it's okay to go to interpret it. If there's no such type and type system says no type error, you are not supposed to run it, just throw a type error, right? Then the programmer can fix the type error and when run the type checking again, and when the type check says okay, then interpret it. That's the usual thing. So as we discussed on Monday again, before interpreting this expression under some environment and get a value or some uncaught exception, we'd better type check that under the type environment, initially empty, and check whether it has some type or not. If it has some type, then when we run it, we are going to have a value of that type. Okay, so far so good. Then let's go back to recursion. Don't worry, I'm not going to read this crazy MKREC again. If you want to, go for it, as you wish. My only point with this code is that before midterm exam, when we talked about recursion, we didn't say anything about type. It was just what? MKREG is some function that takes another function, right? And we can make some function recursive by having this crazy library function. If we want to type check this code, we may want to give some types to these names like mkreg, body, fx, fy, things like that. And I guarantee you that you cannot type check this code. If you don't trust me, yeah, go for it. Go try that. And if you have types for these ... come back to me with the type. Nothing works in place of ... Then what can we do? Right? We discussed this on Monday when we want to have pairs which are really perfectly useful and good language features, and our language did not support that. It just throw on type error. Then it's time to extend the language. When the type system rejects your perfectly good program, then again, your program is perfectly good, right? You didn't make any mistake. Then the type system is bad, meaning the type system is not expressive enough. It's too restricted. Then it may be time to extend the type system to grow up. In this case, we can add the recursive function def as a core form again, meaning we have this def keyword to define a recursive function named faq, which takes only one parameter and of type, yes, of type, now we are talking about types, of type number. Then this factorial recursive function faq takes a number, produces a number. This is the definition, and we can call it. And now that we are adding recursive function to this language, we are going to add if 0 again. Why? Remember, when we have a recursion, we need a way to get out of the loop, right? Recursion meaning recursive call, faq calls faq again. Then we need to have a way to escape like this. So if 0 has this true branch and false branch or true branch, whatever, one branch will have this recursive call and the other branch should be an exit, right? So we will add if 0 to do that. Our language is now called TRFAE. No surprise, right? RFAE with type. So the usual FAE with if 0 and recursive function. This time parameter name has a type annotation, and the return value of this recursive function has this type annotation. And the type language is either number or arrow T. So first good. Then what can you do? We are going to extend this expression to if 0 and recursive function definition. If 0 takes three expressions, condition, true branch, and false branch, as expected, right? And recursion has recursive function name, parameter type, return type, body expression, and an expression to use this recursive function. Yes. If you remember, how did we interpret this code, this language construct? Remember, right? What did we do? If 0, we interpret the first sub-expression for condition, interpret the first sub-expression, and see whether that value is 0 or not. That's why it's if 0. If it's 0, then interpret the second sub-expression, which is a true branch. Otherwise, interpret the last sub-expression, false branch. Note that we didn't check whether the value of this conditional expression, the first sub-expression, is a value or not. Meaning that the value of C could be num_v0 or num_v42 or closure v even. It's not an error in this interpreter. But we don't want that, right? We want to have this if 0, E1, E2, E3, we want this to have num type. But don't worry, because before calling interrupt, we are going to have type check. And if its value is not a number but something different, then we can reject that. We can detect that at compile time by type checking and reject it before calling this interrupt function. Meaning that when we interpret this code, it's already gone. Those code with type errors, that's already gone by type checking. Recursion, recursive function name, parameter type, and return type are ignored because it's interrupt. They are already checked by type check. All we care about is function name, parameter name, body expression, and an expression to evaluate. Then let's make closure V out of this. That's closure V with parameter name, body expression, and the environment. That's clov. But that's not enough because we need to remember the name of this recursive function when we interpret the body. So we need to extend this environment with one more piece of information saying the recursive function f value is closure V, that closure V. And then we replace closure V's first environment with this correct environment. Using this correct environment, interpret that expression. Right? Yeah, now you remember, right? Let's type check that. How can you type check it? If 0 expression takes three sub-expressions and we want that to be well typed, meaning if 0 has three sub-expressions and unlike RFAE, which did not talk about types, TRFAE is talking about types, meaning that it wants to make this first sub-expression to have type number, right? E1 should be either 0 or non-zero numbers, not like non-zero values. That's just our choice. That's the semantics of this language, TRFAE. If you want to have a different semantics, you can define your own language. Today's language that we defined is called TRFAE, which requires the type of the first sub-expression of if 0 be num. Okay? The type of E2, I don't care. But I do care that the type of E2 should be the same with the type of E3. That's it. Then the type of the whole expression is tau. How can we implement that? Let's make sure that the type of the conditional expression is num-t. They should be the same. Then what's next? The type of t and type of f should be the same, right? How can you say that? They should be the same. The type of the true branch and the type of the first branch should be the same. The type of the true branch, the type of the false branch should be the same. Most same, remember we defined that on Monday. Most same takes two types and then check whether they are really same by using this yet another helper function. When they are the same, return the same type. Otherwise, throw an exception by using another helper function. Okay, so far so good. Then finally, how do we type check this? How do we type check this recursive function expression? Recursive function definition. This is the typing rule again. Under some type environment, this recursive function definition and then use, it has this type. Which type? The type is, when we type check this body expression EF, we may use the parameter name which has type tau1. And not only that, but also the recursive function name again, because it's recursive. So then the function xf's type is what? The parameter type to return type. It's all written here. It's from tau1 to tau2. Using those two information, we type check the body expression, and the type of the body expression should be, the return type. If they are different, that's going to be really bad. Then, using that information, we can type check this expression E, but when we interpret or type check this expression E, we cannot use X because it's parameter available only in EF, not in E. So this time, this type environment should have only XF, not X. Clear? Yeah, let's implement that. How do we type check this recursive function definition and use? What's the type of this recursive function? It's an arrow type from parameter type to return type. That's easy. That's a function type. And we are gonna extend this given type environment using that function type, function name and function type. Oh, cool. What's next? The return type tau2 should be the same with the type of function body. Type of function body. Under which type environment? Not only this anti-EMV, but also this. So we need to extend anti-EMV with this parameter type pair. Then finally, what's the type of the whole expression? That's the type of this expression. What's the type of that expression? That's this. Type check that expression under, what was that? Anti-EMV. Now let's take the first break. After the break, we are going to talk about variance.